Welcome to this IROS workshop talk. In the next 30 minutes, I'm going to give you a little bit of insights in how we're using ANYmal in the wild. This is part of the European project Natural Intelligence that has started earlier this year. My name is Marco Hutter, and I'm professor for robotics at ETH Zurich, where we are predominantly working on these quadrupedal platforms, ANYmal. Let's start with the general motivation of legged systems and why we're using them, in particular in the real world. I think today we still have plenty of spaces where we do not have the necessary robotic solutions to be deployed. And what we want to do is create robotic systems that can literally go anywhere to take over some of the dirty and dangerous jobs. These include search and rescue missions that we see on the left, also like lots of underground areas like mines and sewers, where we have to send humans to do some of the nasty work. Offshore areas, construction site, but I think also the latest corona crisis has unveiled that we do not have the necessary robotic solutions at hand today to take over some of these dangerous jobs. And for me, like one of the critical aspects why we do not have that at hand is that robots still lack in mobility and interaction capabilities, in particular if it comes to uncertain environments, so environments that have not been built for robot systems. And this has motivated me for the last decade to do research in the field of quadrupedal systems. We have developed a series of them since 2016. We also created a spin-off company that commercializes some of these machines. You see here on the bottom left, the B version, then the C version, bottom right. And in the image at the very right, we have the ANYmal D version, which is the first fully certified commercial platform that is sold just now by Anybotics. Since we cannot do these workshops in person anymore, I cannot show you this robot. So let me give still a very brief introduction that you know what you're talking about. This is roughly 40-45 kilogram heavy robot, depending on the payload that we put on top. It is driven by integrated actuator units that are fully torque controllable, impact robust, and sealed. We have a simple kinematic linkage with like 3 joints following each other. That makes it easy to maintain and very, very proper to seal. Then in the middle, there is one big main body, one brick, which features all the components you need from like 2 to 3 pieces, network devices, batteries, and so on and so forth. There's a number of perception sensors, Velodyne sensor. There is 6 RGB-D sensors all around, plus 2 wide-angle cameras in the front and the back. And then on top, pan tilt head, which is used as an inspection payload with zoom camera, thermal camera, light, and microphone. Now, the big advantage of legged system, obviously, is that you can go over obstacles, steps, stairs, can move omnidirectionally. But also importantly is that once you may fall, you can then still right yourself up, stand up, and continue to operate. What we have done with the ANYmal platform is that we have put a very strong focus on making it ruggedized. So the machine is fully IP67 proven. That means it can work in dirty environments, it can work in wet environments, as we see here. And it also allows you to do some really fun things like this deployment that we recently did. And I want to show this video simply because we're talking here about natural intelligence, and that gives you a very nice introduction how natural intelligence can be done.
This is the ANYmal. To the untrained eye, it may look like a robot, and that's because it is. But it's no ordinary robot, it's an ANYmal. This ANYmal has just enjoyed an underwater excursion, because it can. The ANYmal is the only robot of its species to be completely waterproof.
So fun aside, most of the developments that we're having today from the Anybotic side, or the commercial developments or applications, are in the field of industrial inspection. You see here 2 cases. On the top right, this is a chemical plant in Germany where the robots are moving around, taking different types of measurements, mapping the environment, localize on this environment, and do these inspection missions over and over again. On the bottom left, we have an offshore deployment in the North Sea, where the robot has been used for many days to do autonomous inspection tasks. And also here, like mapping the environment in teach and repeat fashion, then executing these inspection missions over and over again. Bottom right is construction site operations, where the machine is used for surveying a construction site. And then on the top left, I'll come to that also later in the presentation, this is a deployment that we had in a nuclear power plant in the US as part of the DARPA Sub-T challenge in the urban competition, where the robot is autonomously exploring this environment to create a map and find artifacts in there. Now, in this talk, I will focus on deployments in natural environments, because this is what you're doing in this EU project. ANYmal, there's 4 areas we're looking at, like from forestry over grassland and alpine to dunes. So all places where you already had some ANYmal deployments. I will show you some insights in what is necessary to achieve this. The main challenges that we are tackling here is, from our perspective, on the locomotion navigation side. You have to know that if you are moving in these types of environment, you're typically facing highly unstructured, slippery, rough terrain. You potentially have a lot of obstructions, as in these forests. So what you see is maybe not exactly what you feel, and you have to deal with all of that. You have to deal with that on the locomotion level, but you also have to deal with that on the navigation level. So somebody has to tell you if there's high grass, which looks like an obstacle, that I'm still able to walk through. So there's a lot of semantic understanding that is necessary in order to achieve this. So let's start with control. If you're looking at control, like from a very, very high level structural point of view, what people usually have converted to is that, let's assume legged systems, and I'm talking here about any legged system, can be humanoid, is some sort of a torque controllable multi-articulated system. Now, in order to make that move, you have to have a navigation pipeline that tells you where you can roughly go. You need to have a local planning pipeline that tells you how you move the main body, where I can step, generate some reference motion. And you have a tracking pipeline that really tries to follow that plan while satisfying certain constraints and ensuring reactive behavior. Then you do joint level control, which is typically embedded really on the joint level itself. And obviously, there's also feedback to it. So we have proprioceptive feedback. So everything internally measured, joint position, contact sensors, IMUs that serves as a basis for state estimation. And then also like exteroceptive sensors like cameras and LiDARs, which are used for localization and mapping, also for local terrain mapping that is used to plan and make the system move. Now, the most critical aspect in my eyes is this planning part, where there's lots of research ongoing these days. To give a little more of an understanding of what's going on here, when you're talking about joint level control, you're talking about tens of kilohertz. Tracking is in the orders of kilohertz, while planning, they're really struggling in making this run extremely fast. If you want to run it extremely fast, you have to downscale model complexity, which obviously you sacrifice certain accuracy. On the other hand, if you make the model much more accurate, you will have to downgrade your speed a little bit. The key challenge in here is that we have a hybrid problem. We want to, on one side, plan a continuous motion of how the system is moving. At the same time, you have this discrete problem of where and when to interact with the environment. There has been plenty of works in this, and I really don't have the time to dive into that too much. But from a classical point of view, what we have seen is, historically, people have split up this problem. What we do is we start with certain gait patterns that are predefined, then have some foothold heuristics that tell you where you can approximately step, also depending on the environment perception. You then do, based on this place or this planned footholds, you then do a motion optimization. You pump this through an optimization and you let this motion be tracked. There's also newer research which lumps all of that into model predictive control approaches, where we are optimizing the same time for motion of the system and for the interaction points and the interaction times. Obviously, at the cost that this is slightly slower than that on the left side. And if you do all of that, you can achieve pretty decent locomotion performance, getting across different types of obstacles in a pretty robust manner. However, there is some issues to that, and a lot of these issues you're not really facing if you're not taking these robots and bring them to the most challenging environments you can think of. If you're looking at the real world has lots of things, lots of corner cases that we have some issues in covering with these conventional model-based controllers. Here's some examples where we artificially make the ground very slippery, make the ground moving, where we are in the nature, where the ground just moves away. And robots start to have certain failures. And I'm showing here only videos of our lab to celebrate a little bit our failures, but I could also pull out lots of videos from spots failing, from ghost or unitary robots failing in these types of nasty conditions. The main issues for that, I assume, is that the underlying assumptions of contacts that only occur at feet, terrain that is static and planar, are just wrong. And if you want to overcome this, what people typically are doing, and I'm taking here an illustration of one of Miki's paper. We have a very similar structure, but this nicely summarizes this. What you do is you create lots of ifs, state machines to trigger reflexes, step reflexes, height reflexes. You do slip detection, you do load change detection, you adapt your behavior accordingly. And whenever you count a new corner case, you increase this complexity here. So one of the questions that we asked ourselves is, couldn't we do this a little more in a holistic manner? And that's where machine learning comes into place. So can't we generate all these tricky conditions and then learn a control policy that can deal with that? And for this, we started to work heavily in the field of simulation-based reinforcement learning, then transfer this to the actual physical prototype. You see here some simulations that we did, thousands of robots that we tried to learn them in relatively short time. So what is happening here is that we create a control policy, we gradually increase complexity of the environment to create a curriculum, and the better robots get, the harder we make the environment until they're able to really walk over these types of environments that we're simulating here. We also vary the terrain. I will come to that in a minute, with uneven grounds, with steps, with different types of friction coefficients, different surface pattern. And with relatively short time, obviously lots and lots of data. We're talking about months of data that you would have to collect in real world experiments. You're able to move across these types of environments. Now we took these policies and we deployed them on the physical systems. That's the first thing that started to happen. So we had for a long time, we had issues in bring that to the actual system. And the reason for that is that there is a pretty big reality gap. So what you're simulating is not what is the actual physical system. And the reason for that is that we are assuming in simulation that you have this multi-body dynamics, and then you send the torque command to this multi-body dynamics and get some state feedback. And that's the control policy that we then generating. Obviously, this is not true. In particular, we have actuators in between, which are by far not perfect. They create delay, they have bandwidth limitations, there's saturation there. And all of this is pretty hard to model from first principles. You can do it, but then you have to also slow down your simulation massively, because time constants in electric circuits, in mechanical circuits of motors, just significantly shorter than what we see here. So we have to decrease simulation steps and so on and so forth. So the idea that we had here was that we combine two things here. On one side, we essentially learn this actuator dynamics from experiments. So this should give us kind of a model that represents the difference between simulation and reality. And then we combine on one side something that's difficult to model and easy to learn, like these actuators, with something that is easy to model and difficult to learn, like the multi-body dynamics of your system. You take this, you put this then in an extended reinforcement learning loop, where we on one side stochastically vary our simulation. We then have the integration of these learned models. We have an RL loop to create a control policy, all of that in simulation, and then finally deploy this on the actual physical system. The earlier work that we are doing here, led by Jimin back then, was relatively simple in terms of structure that we need on one side for the actuator net. So you see here, pretty shallow network, only MLP. We then have a very similar structure here for the control policy. Also, this one, not a very complex network structure. And the only way in how we're including here memory is through like a joint state history. So we sample over time the joint states, all the body poses and so on and so forth, and feed this as a history into our control policy. They started to work out very beautifully. We could suddenly move with high efficiency, a lot faster than previously, a lot more robust. If you have external disturbances, push, pulls, whatever, it is becoming a lot more robust than what you've seen before in model-based experiments. If you're interested in this more details, we have the simulator is available for the research community, also the whole gym that you can start playing around and testing this by yourself. What you can see here, nonetheless, is still in flat grounds and indoor environments. You're going to see later in how we are extending this to real-world conditions. The cool thing is now you can not only start walking around, but you can also start doing more complex maneuvers, self-rightening, standing up, locomoting, and bring this even together in a hierarchical learning fashion, and you can generate behaviors like this. So robots that are falling over are able to stand up and continue to operate. You can actually pull down the robot to a pretty much arbitrary configuration on the ground that you'll find a way to stand up from that and continue to operate. So we haven't seen an equally robust behavior afterwards, even in the best model-based controllers that are out there. The key ingredient for that was that we have a simulation and reality which match pretty accurately. So here is the two of them with the same initial conditions in control policy. That obviously allows you to do now many different things with that. As I said, this is still all flat ground. We want to deploy it in real world, in natural environments, where we have a huge variety of grounds. And this variety of grounds is actually, in my eyes, impossible to model in simulation. It's very hard to sense for perception. And even if you could simulate this, the question remains is what is actually important for locomotion? What is the information I want to extract from the environment and use that in order to locomote with my system? So the method that we were applying here is called privilege training. So what you do is we first train a teacher policy, and this teacher policy has access to any information of the environment which may be important. Contact states, contact forces, terrain profiles, friction coefficients, disturbances, and whatever. We then use an MLP encoder to create some latent information. We train using a policy gradient method, standard TRPO, an MLP that defines the action that go to our system. Now, obviously, we don't have access to this privileged information on the actual system once we deploy it. The idea that we included in here is that we can now train a student policy in a second step, which tries to extract this latent information, not from the privileged information, but this latent information from a history buffer of all types of proprioceptive measurements, so everything like internal states of the robot through a TCN encoder. And we're imitating the same action by taking the same MLP as the policy and then learn this TCN encoder to kind of generate the same latent information. You do this again with the so-called curriculum learning. So you initialize the whole thing. The better the robot becomes, the harder you make the environment. And you do this over a variety of different environment conditions, steps, inclinations, changing frictions, stairs. And after a few thousand iterations, you're able to have the robot move. That's actually really a zero-shot generalization to the real deployment. So here, robot walking in reality over terrain it has never seen before, not even in simulation, but somehow this environment has become kind of a subset of what we were simulating before. And that was the starting point, that we are able to release this robot into the wild. We could walk over all kinds of different grounds, through rivers, slippery terrain that is actually even not perceivable by any perception sensor. You can take it to the forest and move through vegetation, as you can see here. There's lots of interesting findings that are here under the hood. I want to illustrate here a few of them. First one is here, the robot is walking on a wet whiteboard, which is extremely slippery. You see it moving. Once you're stepping on the surface, it starts sliding. Now, what we do here is we encode from this latent information what is the friction coefficient that the robot assumes. And you see that it assumes a relatively high friction coefficient. Once you're stepping on a surface, the estimation of the friction coefficient immediately drops to a very low value. The robot adapts its behavior, so it walks a lot more cautious on the the low friction surface. And then after leaving, it starts feeling that friction coefficient might be higher, and it slowly ramps it up again. And actually, this is very similar to how we would behave, right? Once you're stepping on a slippery surface, you immediately stiffen up, you walk differently, and then you carefully figure out whether the environment has a high traction again, and then you can move as you were moving before. A second nice finding is that you can move across steps without seeing them. So here the robot moves, it doesn't see the steps, so perception is turned off. And what happens is that it moves. Now it hits this obstacle, it memorizes this and triggers a reflex a step higher. We can actually show this again. If we decode, we see the assumption of the terrain height in front of the robot. As soon as it hits it, we have an estimation which is significantly higher uncertainty. And again, once you're stepping on it, it then consolidates its opinion and moves with that assumption of the terrain. And you can do this also while adding payload. And here actually even the payload is estimated while the robot is moving. Now this is all blind. One would ask, if you have here a step and you have perception sensors, why the hell do you walk blindly? You can just integrate this into your controller. And that's actually true. So this is also what we're doing. So you can take the elevation of your environment and you include this directly into your control policy. That works well as long as you have a good elevation map. The problem is that in most situations, once you're going to real world settings, you cannot count on a good elevation mapping. You can have reflective ground, you don't see anything. You may want to move through deep snow, and there's also like no data available or like completely wrong data. You might have overhanging objects that are still occurring somehow in your map. Non-rigid obstacles, which you move through vegetation. There's like obstacles that appear to be a geometric obstacle, but once you step on it, it's not really something you can step on. You can have pose estimation drifts, and that creates also issues with how the environment looks like for the robot. You may have exclusion. If you have steep stairs, you may not see certain areas, you don't know how it is there. So I cannot talk too much about how exactly we're solving this, because this is a paper that is still under review. But what you're doing is similarly in simulation, you generate noisy height scan drifts with all these different conditions that may occur, and have the robot figure this out or learn to deal with that by itself. And this was really a milestone that allowed us to now take the robot to arbitrary environments where the robot needs to see the environment, but still be robust against adverse perception conditions. You have here a couple of examples of the machine moving in rough terrain environments. That was also an enabler for us to do things like walking on stairs, turning on stairs in pretty much arbitrary directions. And we can now take the robot and bring it to natural environments. Here is a hike that we were doing with the machine, where we took it on a 1 hour hike, 35 minutes up, 35 minutes down, and the robot moved with this exact pace that was originally planned for human walkers. So you can see here going upstairs, like a zero interaction by humans. And there is plenty of cases where it's a pretty tough environment for a robot to move. Now, so far, this was all human handcrafted or like human guided navigation. We have a human operator with a joystick that tells the robot more or less where to go. Obviously, you want to do this autonomously. You want to find the right locomotion path. For this, you need to have first a traversability estimation that tells you where can I move and where not. And once you have this, you then find the best path. For traversability estimation, what people were doing historically is that you take an elevation map of the environment and then you define certain criteria. You know, you don't want to move in slopey terrains, in high roughness, at step heights. You create certain cost criteria and generate a traversability map. We went a bit of a different direction. Like, this is a lot of human handcrafting, but the human is actually extremely good in telling the robot, well, you can walk there or you can't walk there. So what we're doing is we took a number of images of or elevations of the environment, and I had the human supervisor just labeling them, labeling what are areas that you can walk on, areas that you should not walk on. And from relatively little data, you're able to then learn and extract certain cost functions that tell you where you can walk and where not. Once you have this traversability estimation, you then can find the best path. Here's one of the example work by Lorenz of terrain navigation, where we essentially apply a reachability-based planner where the torso, here labeled in blue, is planned to have always contact-free motion with the environment, while the feet have a reachability shape. They always have to be in contact with traversable terrain. We then implemented here a lazy PRM method, which maintains a goal-agnostic planning graph. It can do a lot of things in the background, such that once you have a new waypoint, you could just query from your pre-calculated roadmap what is the optimal path to go to this new waypoint, and by that also make it efficient. Now, in here, everything was done like human supervised, either by generating this cost function or by labeling data. We also started a way in moving the similar direction as with our learn control policy, namely to learn a traversability estimate. We know that the local terrain patch essentially determine where you can walk and where not. And we, as human supervisors, we track certain features that tell us whether you can move efficiently, how much time it takes, or how likely it is to fall. So what we want to do here is that we want to generate the same thing, but also based on simulation. So we are simulating the robot over arbitrary terrain, and we train a feature extractor method plus a local motion cost predictor that, depending on the goal we're getting and the local features, determines what are the individual costs we have here. And we train this in simulation over all kinds of different environments. And then once we're deploying the machine, all we need to do is you take the map of the environment, and we can automatically do track the features and estimate the costs. We do this using a sampling-based planner. So depending on the command we're giving, you can extract the costs from this pipeline. You can even do then an iterative gradient-based optimization afterwards. And we do all of that in a batch processing, with everything is also running very fast. With this at hand, you're able to have an autonomous navigation on the robot. So give it certain waypoints and it'll automatically go there. So you can see how the robot maps the environment, creates the elevation, and then moves it to the target location. Now, so far, we have only talked about geometric obstacles. For me, the question is really, how do we handle this now once we're in very natural environments? Which terrain should we walk across? It might look geometrically exactly the same. And what we did for this is that we let the robot explore the environment and identify itself what is a good foothold and what is a bad foothold, depending on how the terrain felt like. So we collected, while moving, we collected force torque signals, IROS signals to generate certain labels of the different types of environment. At the same time, while moving around, you know that what I see now, I'm stepping on in a second. So afterwards, I have stepped on, I collect the data, I know how that foothold has looked before. So we can use this in order to label the images and then train a terrain property predictor that we then deploy on the actual system. So here you have that being deployed. You have the input image with the footholds that are classified as good and bad. And then from that, you can generate the ground reaction score. And you see, like, from relatively little data, only RGB, you can also very nicely distinguish what is a street, what is ground I should walk on and what not, and then use this as a cost for during a navigation problem. So if you have your goal point in the back and you have the robot just walking to that goal point, and it automatically now selects terrain that is better to walk on and only starts traversing less good terrain once it has to in order to achieve the goal position. So this is more or less the pipeline we need for autonomous local navigation. What is missing now to make the whole thing completely autonomous, that we have to have a global localization and mapping pipeline, and then apply on top of that a planner that tells us on a global scale where should I move and where not. And this is the last two elements. I don't have time to go too much into details, but that's what we were deploying in many of the missions that you see from our lab. So on one side, there's a complementary SLAM solution that we're combining different types of measurements from LiDARs, Lego odometry, and visual odometry. Plus, there's a volumetric exploration planner that was developed primarily by Costas Alexis groups at ANYmal that we use in order to have the robot autonomously explore. And that was the solution we applied also last week during the DARPA Sub-T challenge. Here is an earlier video of the robot exploring an underground area. You see how the machine maps the environment, how it creates a 3D map, and then depending on where it can have more volumetric gain, it adapts the path and moves to a different location. We can do this for a pretty long time. So we had hour-long missions covering kilometers of distances in a fully autonomous fashion. But last week during the finals, what we deployed was 4 ANYmals together in these underground areas in the US. You see here in this video a few highlights of how the robot was moving there. To a large extent was autonomous with the pipeline that I've just illustrated you in this talk before. And the machine was capable to move robustly, reliably, without falling on pretty challenging rounds with different types of obstacles. We also had lots of obstructions, so fog was pumped or artificial smoke was created such that we had bad perception. And in contrast to many other legacy systems that are used there, the machine here was just able to move very robustly and reliably around. For me, the most exciting outcome of this DARPA Sub-T challenge, and this is the ranking that we had at the very end, is that from all teams that participate in the systems competitions, the top 6 of them, they were using Legged machines. And I think this is clearly the future of where we want to go with field robotics. Legged machines seem to be a very, very promising solution. With this, I'm done with my 30 minutes. Thank you very much for your attention. In particular, big thank you for the NI folks for organizing this, for organizing a fantastic project. I'm looking very much forward to be part of that in the near future. If you're interested in more information, check out our code repositories, our homepage, and our YouTube channel. And I'm happy to have a discussion with you later this afternoon. Thank you very much.